Let's talk a little bit about this inner product. So the inner product is a very important property of our Hilbert space. It's the equivalent of the dot product in Rn. It gives us a number from any two vectors. So if I have one vector, which might be some linear combination of h and v, and I have another, so that's a vector. If I have another vector, which is a different combination of h and v, then the inner product between these two, we would write like this. It matters which way around we put it. That would be alpha star alpha 2 plus beta star beta 2. So it's a complex number and you can get it straight from the coefficients. Of course you can get anything computed from the coefficients if you wish. Now this notation should be slightly reminiscent of the equivalent notation for Euclidean inner products, where if you have the inner product between these two objects, we know exactly how to write that in terms of the coefficients. And you'll note that this is different to that, so we have a different method of producing these inner products. In fact, technically, while this object here is a vector, it's a vector which is an element of our vector space. In this case, it's the position vector in R3. This object here is actually slightly different. This is a covector, which is an element of our dual space. What, you might ask, is a dual space? Formally, a dual space is just the space of linear functionals on our vector space. In fact, in the case of Euclidean vectors like this, it was so similar in structure to our vector space that we didn't even really notice the difference. All we need to describe the completely arbitrary linear map on this vector is three numbers, and we just happen to arrange them like this, and we can use our matrix multiplication to extract anything we like. But formally, the fact that this is a different shape actually does affect the kind of matrix rules that we can apply, and so technically it is a different space. We didn't care about that at all, really, when we were talking about Euclidean vectors. But now that we're talking about these vectors, if I was to represent this in the HV basis as just a little vector, so this one would be alpha, and this one would be alpha 2, because this is our vector, and beta 2, then actually, in order to represent this thing as the appropriate covector, remember for this one, all we did was we just rearrange the numbers. This one, we almost do that. We rearrange the numbers, so we take our alpha and our beta, and we put them in a row, but we also take the complex conjugate. Now this process of going from a vector to a covector is called Hermitian conjugation. And after you've done Hermitian conjugation, you've taken the Hermitian conjugate of something. So the Hermitian conjugate of this state here, we denote with this symbol, which raised to a dagger. And that's just equal to this object here, the covector. Now, because of their tendency to form brackets, like that, we call this a ket, and that's a bra, ket. There we go. I apologize for my discipline's sense of humor. If we take the Hermitian conjugate of just a complex number, then that's just the complex conjugate. It's entirely reversible. If I take the Hermitian conjugate of a bra, I get the corresponding ket. If I take the Hermitian conjugate of a number times a state, I get the Hermitian conjugate of each thing multiplied by each other. In general, if you have a bunch of things that don't commute, so I can put this scalar on either side of my vector and it works fine, then I actually have to reverse the order when I take the Hermitian conjugate. For example, let's take the Hermitian conjugate of this inner product. It's quite clear that if I did this the other way around, I wouldn't get exactly the same answer. But our notation is consistent. If I was to swap those around, I would get a complex conjugate and everything. And here, of course, I will exactly get. And you see when we turn this around, this is just a number. So if we take the Hermitian conjugate of it, we just get the complex conjugate. And so when we turn it around, we clearly just get the complex conjugate. One final comment about using bras and kets to do inner products. We often do things in terms of just the coefficients like we did in these matrix multiplications for Euclidean space and this matrix multiplication. But the coordinate basis version is not always the correct way to go. And you can always do things, if you wish, directly. So if I take these two things here, I can quite legitimately expand them out. So this thing on the left is alpha star with my h as a bra, and beta star with my v as a bra. And I can always expand these things out linearly. And if I now look at these things here, these objects here are the inner product between basis vectors, h and v. Now, of course, for a basis to be called a basis, all it really needs to be is a spanning set that's linearly independent. But we often, and for example in these kinds of position vector cases, we often talk about the basis set as being more than that, but actually orthonormal. So the inner product between H and H, by definition, if it's normalized, if these are normalized vectors, then the inner product between them is 1. So this will be 1, and this will be 1. And if they're orthogonal, which is the ortho part of orthonormal, then the inner product between any two different ones is 0. So these two terms would be 0, and these two terms would be 1, and we come back to our original result. In general, when we talk about bases, we can always choose, and we usually do choose, to talk about an orthonormal one. In general, what that's going to look like is if I have a set like this, then if I take an inner product between any two of them, then that's going to be 0 if these indices are different, and 1 if they're the same, so this would be the Kronecker delta. For a continuous index, it works very similarly, except of course we can't use the Kronecker delta, we have to use the Dirac delta.